Beyond our pale blue dot, suspended in the cosmic dark, thousands upon thousands of worlds orbit distant stars. These exoplanets, as we call them, drift through space like silent possibilities, each one a potential chapter in the story of life itself. Some are scorching furnaces where metals rain from the sky. Others are frozen worlds wrapped in perpetual twilight. And somewhere among them, perhaps closer than we dare to hope, might be planets where life stirs in alien oceans, where storms carry the chemistry of possibility, where evolution writes its own unique poetry across landscapes we can barely imagine. Hi, I'm Luna, and if you find comfort in quiet curiosity, gentle science, and stories that drift like starlight, you're in just the right place. So wrap yourself in something warm, settle in. And if you'd like to hear more sleepy wonderings, feel free to like and subscribe, because tonight, we're traveling beyond our solar system to explore worlds that circle other stars, worlds that might harbor the greatest discovery in human history: life beyond Earth. The universe has been generous with its planets. In our galaxy alone, astronomers estimate there might be over 100 billion worlds, each one shaped by the particular dance it performs around its star. Some hurtle through their orbits in mere days, so close to their suns that their surfaces glow like embers. Others take centuries to complete a single year, wandering through the cold reaches where starlight barely whispers across frozen landscapes. Between these extremes lie the worlds that capture our imagination most deeply. Planets that exist in that gentle zone around their stars, where liquid water might pool on their surfaces, where the temperature allows for the delicate chemistry that we know can give rise to life. When we search for potentially habitable exoplanets, we're really searching for mirrors of our own world's journey. Earth wasn't always the living planet we know today. For the first billion years of its existence, it was a harsher place, pummeled by asteroids and comets, its atmosphere toxic to most life forms we recognize today. The oxygen we breathe was actually created by ancient microorganisms that transformed our planet's chemistry over hundreds of millions of years. As we gaze out at distant worlds, we're looking for places that might be at any stage of this profound transformation. The story of exoplanet discovery begins with patience and mathematics. For decades, astronomers knew that other stars likely hosted planets, but proving their existence required detecting the incredibly subtle effects these distant worlds have on their parent stars. Imagine trying to spot a firefly circling a lighthouse from thousands of miles away. That's the challenge astronomers faced when they first began hunting for planets around other stars. The breakthrough came through two primary methods, each as elegant as it is ingenious. The first, called the radial velocity method, relies on the fact that planets don't simply orbit their stars, they dance with them. As a planet moves around its star, it tugs gently on that star with its gravity, causing the star to wobble ever so slightly. This wobble changes the color of the star's light in ways we can detect with sensitive instruments, the same way the pitch of a train's whistle changes as it approaches and then moves away from you. The second method, transit photometry, watches for the brief dimming that occurs when a planet passes directly between its star and Earth, like a tiny eclipse. These dips in starlight are incredibly subtle, typically reducing a star's brightness by less than 1%. But they tell us remarkable things about the worlds that cause them. From the depth and duration of these transits, we can calculate a planet's size, its orbital period, and even begin to understand what its atmosphere might be made of. The Kepler Space Telescope revolutionized our understanding of planetary systems by staring unblinkingly at a patch of sky containing over 150,000 stars, watching for these telltale dimming events. For nearly a decade, Kepler monitored these stars with extraordinary precision, discovering that planets are not rare cosmic accidents, but common features of stellar systems. In fact, nearly every star in our galaxy appears to host at least one planet, and many harbor entire families of worlds. What Kepler found challenged many of our assumptions about how planetary systems form and evolve. We discovered hot Jupiters, gas giants that orbit their stars in a matter of days, their atmospheres heated to thousands of degrees. We found super-Earths, rocky worlds larger than our own planet, but smaller than Neptune, a type of world that doesn't exist in our solar system, but appears to be one of the most common kinds of planets in the galaxy. We observed planets with years that last just hours, and others with orbits so elliptical that they experience seasons of fire and ice. Among all these exotic worlds, astronomers have identified several thousand planets that orbit within their star's habitable zone, that region where temperatures allow liquid water to exist on a planet's surface. This habitable zone, sometimes called the Goldilocks zone, isn't a fixed distance from a star, but depends on the star's size and temperature. Around small, cool red dwarf stars, the habitable zone lies much closer in than it does around larger, hotter stars like our Sun. Red dwarf stars have become particularly interesting to astrobiologists because they make up about 75% of all stars in our galaxy and burn so slowly that they can maintain steady energy output for trillions of years, hundreds of times longer than our Sun will shine. This longevity might provide the vast timescales necessary for life to evolve from simple chemistry to complex organisms. However, planets around red dwarfs face unique challenges. Because they orbit so close to their stars to stay warm, they likely become tidally locked, with one hemisphere permanently facing their star and the other locked in eternal darkness. Imagine standing on the day side of such a world. The red dwarf star would hang motionless in the sky, a vast crimson eye that never sets, never moves. The landscape around you would be painted in perpetual sunset colors, deep oranges and purples stretching to horizons where the terminator, the boundary between day and night, creates an eternal twilight zone. On the night side, temperatures might plummet hundreds of degrees below freezing, while the day side could be hot enough to boil water. Between these extremes, in the twilight region that rings the planet, temperatures might be just right for liquid water to flow. This twilight zone has captured the imagination of scientists studying planetary habitability. Here, neither scorching heat nor bitter cold dominates. Warm air from the day side might create persistent winds that carry heat toward the night side, while cool air flows back to replace it, creating global circulation patterns that could moderate temperatures across the entire planet. Some models suggest these worlds might have vast ice sheets on their night sides and steamy, cloudy day sides, with temperate regions in between where rivers flow and weather systems develop. One of the most intriguing, potentially habitable worlds discovered so far is Proxima Centauri b, a planet orbiting the star nearest to our Sun. At just over 4 light-years away, Proxima b is practically next door in cosmic terms. This world receives roughly the same amount of energy from its red dwarf star as Earth receives from the Sun, placing it squarely within the habitable zone. While we don't yet know whether it has an atmosphere or liquid water, its proximity makes it a prime candidate for detailed study with future telescopes. The TRAPPIST-T-1 system represents perhaps the most exciting discovery in exoplanet science to date. This small red dwarf star, located about 40 light-years from Earth, hosts 7 Earth-sized planets packed into orbits that would all fit within Mercury's orbit around our Sun. 3 of these worlds lie within the habitable zone, and they're so close to each other that if you stood on one, the others might appear larger in the sky than our Moon appears from Earth. The planets are likely tidally locked to their star, but their close proximity means they exert significant gravitational influences on each other, potentially creating tidal heating that could drive geological activity and maintain liquid oceans, even on the more distant worlds. The James Webb Space Telescope has begun to reveal the atmospheric compositions of some of these worlds, and early observations suggest complex chemistry in their upper atmospheres. Water vapor, carbon dioxide, and other molecules associated with habitability have been detected in the atmospheres of several exoplanets. These observations represent our first steps toward answering one of humanity's most profound questions. Are we alone in the universe? When we consider what makes a planet habitable, water often takes center stage, and for good reason. Water is an exceptional solvent, capable of dissolving a vast array of chemicals and facilitating the complex reactions necessary for life. It remains liquid over a relatively wide range of temperatures and pressures, provides a medium for organic molecules to interact and combine, and has unique properties that help regulate temperature on planetary scales. But habitability encompasses more than just the presence of liquid water. A truly life-friendly world needs a stable climate over geological timescales, protection from harmful radiation, and the right mix of chemical elements necessary for building complex organic molecules. Earth's magnetic field, generated by its molten iron core, deflects most of the harmful charged particles streaming from the sun. Without this protection, our atmosphere would gradually be stripped away into space, as appears to have happened to Mars billions of years ago. The composition of a planet's atmosphere plays a crucial role in determining its habitability. Carbon dioxide acts as a greenhouse gas, trapping heat and warming a planet's surface, while also providing the carbon that life uses to build organic molecules. Oxygen, though toxic to many early forms of life, eventually became essential for complex organisms that could harness its reactive properties for energy. The balance between these and other atmospheric gases determines not only a planet's temperature, but also its ability to maintain liquid water at its surface. Some of the most potentially habitable exoplanets discovered so far challenge our Earth-centric assumptions about where life might arise. Kepler-452b, often called Earth's cousin, orbits a star similar to our Sun in a 385-day year. This world is about 60% larger than Earth and receives roughly the same amount of energy from its star that Earth receives from the Sun. If it has a substantial atmosphere and liquid water, Kepler-452b might experience seasons and weather patterns somewhat similar to our own planet. 715b presents a different model of habitability. This super-Earth, about 50% larger than our planet, orbits a nearby red dwarf star every 19 days. Despite its rapid orbit, it lies within the conservative habitable zone of its star. If this world has retained a thick atmosphere, greenhouse warming might create surface conditions suitable for liquid water. The discovery of a second, potentially habitable planet in the same system makes it even more intriguing as a target for future atmospheric studies. The search for biosignatures, chemical signs of life in exoplanet atmospheres, represents the next frontier in exoplanet science. When starlight passes through a planet's atmosphere during a transit, different molecules absorb light at characteristic wavelengths, creating a spectroscopic fingerprint that reveals the atmosphere's composition. Oxygen and water vapor together might indicate biological processes, while simultaneous detection of oxygen and methane would be particularly compelling. Since these gases react with each other and disappear quickly unless constantly replenished, the James Webb Space Telescope has the sensitivity to detect these biosignatures in the atmospheres of nearby Earth-sized planets, marking the first time in human history that we have the technological capability to search for signs of life beyond our solar system. Early observations have already revealed water vapor in the atmospheres of several hot gas giants, demonstrating the telescope's ability to analyze exoplanet atmospheres in unprecedented detail. As we venture deeper into the realm of potentially habitable worlds, we encounter planets that might support life in ways we're only beginning to imagine. Some models suggest that planets with thick atmospheres of hydrogen and helium, so-called Hycean worlds, might maintain liquid water oceans beneath their dense atmospheres, even when orbiting far from their stars. These worlds could be several times larger than Earth, while still maintaining surface conditions suitable for life. Ocean worlds represent another intriguing possibility. In our own solar system, moons like Europa and Enceladus harbor vast oceans beneath their icy surfaces, heated by tidal forces from their parent planets. Similar processes might occur on exoplanets, particularly those in multi-planet systems, where gravitational interactions could drive tidal heating for billions of years. These subsurface oceans might be even more conducive to life than surface water, because they're protected from harmful radiation and atmospheric loss, while maintaining stable temperatures over geological timescales. The atmospheres of potentially habitable exoplanets might look quite different from Earth's current atmosphere. Early in our planet's history, before oxygen-producing cyanobacteria evolved, Earth's atmosphere was dominated by methane, ammonia, and carbon dioxide. A young exoplanet might maintain such reducing conditions for billions of years, potentially supporting forms of life based on different chemical pathways than those we see on modern Earth. Some researchers have suggested that planets with methane-rich atmospheres might develop organic hazes in their upper atmospheres, creating complex hydrocarbon chemistry that could serve as a pathway to life. The concept of planetary habitability has expanded significantly as our understanding of life's limits has grown. Extremophiles on Earth, organisms that thrive in conditions once thought incompatible with life, have shown us that life can adapt to extraordinary circumstances. We've found organisms living in the scalding waters around deep-sea volcanic vents, in the frozen valleys of Antarctica, in highly acidic environments, and even in rocks miles beneath Earth's surface. These discoveries suggest that the habitable zone around stars might be much broader than previously thought, encompassing worlds that seemed too hot, too cold, or too chemically extreme to support life. The study of tidal forces on exoplanets reveals another layer of complexity in determining habitability. Planets that orbit close to their stars experience strong tidal forces that can create significant heating within their interiors, while extreme tidal heating might render a planet uninhabitable by triggering runaway volcanism. Moderate tidal heating could provide energy for geological processes that help maintain a stable climate and recycle essential elements between a planet's surface and interior. The rotation rate of a planet also influences its habitability in subtle ways. Earth's 24-hour day creates a regular cycle of heating and cooling that helps drive atmospheric circulation and weather patterns. Planets with very slow rotation might develop extreme temperature differences between their day and night sides, while rapidly spinning worlds might experience such violent weather systems that surface conditions become chaotic and unstable. Magnetic fields add another dimension to planetary habitability. While Earth's magnetic field protects our atmosphere from erosion by the solar wind, not all potentially habitable planets need strong magnetic fields. Planets with very thick atmospheres might be able to withstand atmospheric erosion even without magnetic protection, while worlds orbiting quiet, stable stars might face less aggressive stellar winds than planets around more active stars. The search for potentially habitable exoplanets has revealed that planetary systems come in configurations quite unlike our own solar system. Many stars host families of planets, packed much closer together than the planets in our system, with orbital periods measured in days or weeks rather than months or years. These compact systems might actually be more conducive to habitability than systems like ours, because planets can exchange materials through collisions with asteroids and comets that travel between worlds, potentially spreading life from one planet to another, a process called panspermia. Some of the most Earth-like exoplanets discovered so far orbit stars that are older than our Sun, raising fascinating questions about the evolution of life over cosmic time. If life arose on these worlds billions of years ago, what stage of development might it have reached by now? On a planet where life has had a several billion-year head start on Earth's timeline, evolution might have produced organisms and ecosystems that dwarf anything in our experience. The atmospheres of these ancient worlds might tell stories of biological evolution played out over vast timescales. On Earth, the rise of oxygen-producing photosynthesis fundamentally changed our planet's atmospheric chemistry and enabled the evolution of complex, multicellular life. An exoplanet with billions of additional years of biological evolution might have undergone multiple such transitions, creating atmospheric compositions that reflect the accumulated effects of life over geological ages. Climate stability emerges as one of the most important factors in long-term habitability. Earth has maintained liquid water on its surface for nearly 4 billion years despite gradually increasing solar luminosity, largely due to feedback mechanisms that help regulate global temperature. As our sun has grown brighter over time, increased plant growth has removed carbon dioxide from the atmosphere, reducing greenhouse warming and keeping Earth's climate relatively stable. Exoplanets around different types of stars face different challenges in maintaining climate stability. Planets orbiting red dwarf stars might benefit from their host star's extremely long lifetime and stable energy output, but they must contend with potentially intense stellar flares and the effects of tidal locking. Planets around sun-like stars might enjoy more stable conditions, but have a limited time window, perhaps a billion years or less, before their star evolves and becomes too bright to maintain habitable surface conditions. The role of plate tectonics in maintaining habitability has become increasingly appreciated as we study potentially habitable exoplanets. On Earth, the slow motion of crustal plates helps regulate global climate by controlling the amount of carbon dioxide in the atmosphere through volcanic outgassing and weathering processes. Plate tectonics also helps maintain Earth's magnetic field by keeping the planet's interior hot and driving convection in the molten iron core. Whether exoplanets can develop and maintain plate tectonics depends on many factors, including their size, composition, and thermal history. Super-Earths, planets larger than Earth, but smaller than Neptune, might be more likely to have active plate tectonics because their greater mass provides more internal heat to drive geological processes. However, if a super-Earth is too large, increased pressure in its interior might actually inhibit plate tectonics by making the rock too stiff to flow. The moons of potentially habitable exoplanets represent another frontier in astrobiology. Large moons can help stabilize a planet's rotation axis, preventing extreme climate variations caused by shifts in seasonal patterns. They can also create tidal forces that drive geological activity and might even be habitable in their own right. A large moon orbiting a gas giant in the habitable zone might provide an Earth-like environment with the added benefit of spectacular views of its parent planet hanging in the sky. Binary star systems, where two stars orbit each other, host a surprising number of potentially habitable planets. These complex gravitational environments create unique challenges for planetary formation and evolution, but they might also provide interesting opportunities for habitability. A planet orbiting both stars of a close binary system would experience two sunrises and sunsets each day, with complex seasonal patterns determined by the planet's orbit around the binary pair and the stars' orbit around each other. Some planets in binary systems orbit just one of the two stars, creating conditions where a second sun appears as an extremely bright star in the sky. These worlds might experience additional heating from the distant companion star, potentially expanding the habitable zone and creating more opportunities for liquid water to exist on planetary surfaces. The chemistry of planet formation plays a crucial role in determining which worlds might develop the conditions necessary for life. Planets that form in the outer reaches of their stellar systems, where water and other volatile compounds can condense into solid form, might migrate inward over time, carrying these essential ingredients with them. This process could deliver vast amounts of water and organic compounds to worlds that originally formed too close to their stars to retain these materials. Conversely, planets that form in the inner regions of stellar systems might accrete material from asteroid and comet impacts over millions of years, gradually building up inventories of water and organic compounds necessary for habitability. The timing and intensity of this late heavy bombardment could determine whether a planet develops a stable hydrosphere or whether its surface water is lost to space through impact heating and atmospheric erosion. The diversity of potentially habitable exoplanets challenges us to expand our thinking about what alien life might look like. Life on a tidally locked planet might adapt to the extreme temperature gradients by migrating seasonally between different climate zones, or it might evolve to take advantage of the stable conditions in the twilight zone between permanent day and night. Organisms on high-gravity super-Earths might develop very different body plans than life on Earth, while creatures adapted to the thick atmospheres of Hycean worlds might thrive in environments we would find completely alien. The atmospheric chemistry of potentially habitable exoplanets might support forms of photosynthesis quite different from what we see on Earth. Plants around red dwarf stars might evolve to capture the abundant infrared radiation these cool stars emit, potentially appearing black or very dark red rather than green. Life on planets with methane-rich atmospheres might develop metabolisms based on different chemical reactions entirely, using sulfur or nitrogen compounds as energy sources instead of oxygen. Seasonal patterns on exoplanets could drive biological cycles in ways we're only beginning to imagine. A planet with a highly elliptical orbit might experience extreme seasons lasting hundreds of Earth days, creating environments where life must either migrate vast distances, hibernate for extended periods, or adapt to enormous temperature swings. These challenging conditions might actually accelerate evolution by constantly selecting for organisms capable of surviving changing environments. The search for biosignatures in exoplanet atmospheres represents humanity's first serious attempt to answer the question of whether we're alone in the universe. The detection of oxygen and water vapor in a planet's atmosphere would suggest the possibility of life, but confirming biological activity would require multiple independent lines of evidence. Scientists are developing sophisticated models to distinguish between biological and non-biological processes that might produce similar atmospheric signatures. The philosophical implications of discovering life on an exoplanet would be profound. Finding even simple microbial life would demonstrate that the processes that led to life on Earth are not unique, suggesting that life might be common throughout the universe. Discovering complex life or signs of intelligence would represent perhaps the most significant moment in human history, fundamentally changing our understanding of our place in the cosmos. As we continue to discover and characterize potentially habitable exoplanets, we're also developing the technologies that might someday allow us to visit these distant worlds. While the nearest potentially habitable exoplanet is still over 4 light-years away, a distance that would take our fastest current spacecraft tens of thousands of years to traverse. Concepts for interstellar travel are advancing from pure science fiction toward engineering possibility. Breakthrough Starshot and similar initiatives are exploring the possibility of sending tiny robotic probes to nearby exoplanets using powerful lasers to accelerate lightweight spacecraft to a significant fraction of light speed. These miniature explorers might reach nearby star systems within decades rather than millennia, providing our first close-up images of potentially habitable exoplanets, and perhaps even detecting signs of life directly. The study of exoplanet atmospheres is revealing the complex interplay between stellar radiation, planetary composition, and atmospheric chemistry that determines habitability. Some planets that initially appeared to lie within their star's habitable zone might actually be too hot to maintain liquid water due to runaway greenhouse effects, while others that seemed too cold might stay warm enough for habitability through greenhouse heating from thick atmospheres of carbon dioxide or other heat-trapping gases. The concept of habitability continues to evolve as we discover more about the extreme environments where life can survive. Recent discoveries of organisms living in Earth's deep subsurface, sometimes miles beneath the surface, have expanded our understanding of the deep biosphere and suggested that habitable environments might extend far into planetary interiors. Exoplanets with thick crusts and subsurface oceans might harbor vast ecosystems completely isolated from their surface environments. Atmospheric escape processes play a crucial role in long-term habitability, particularly for planets orbiting active stars. High-energy radiation from young or flare-prone stars can gradually strip away planetary atmospheres over billions of years, potentially transforming once habitable worlds into barren landscapes. Understanding these processes helps astronomers identify which potentially habitable exoplanets are most likely to have retained the atmospheric conditions necessary for life. The magnetic fields of exoplanets remain largely mysterious, but they might be detectable through radio observations of particle interactions between stellar winds and planetary magnetic fields. Strong magnetic fields could indicate active geological processes in a planet's interior, suggesting the kind of long-term geological activity that helps maintain habitable surface conditions. Alternatively, some planets might maintain habitability without magnetic fields by relying on thick atmospheres or other protective mechanisms. The Goldilocks zone concept has expanded beyond simple temperature considerations to encompass the complex web of factors that contribute to long-term habitability. The galactic habitable zone considers a star system's location within our galaxy, avoiding regions with too much radiation from supernovae or too few heavy elements for rocky planet formation. The temporal habitable zone accounts for the evolution of stellar brightness over time and the limited window during which planets can maintain stable climates. Some researchers have proposed that moons might actually be more likely to harbor life than planets, particularly in systems where massive gas giants orbit within their star's habitable zone. These giant planets could host multiple large moons, each potentially habitable, effectively multiplying the number of worlds where life might arise in any given system. The tidal heating from orbital interactions might provide additional energy sources for biological processes. The diversity of stellar environments where potentially habitable planets have been found continues to surprise astronomers, from systems with planets orbiting both stars of a binary pair to worlds around ancient metal-poor stars formed when the universe was much younger. Life might find ways to arise and thrive in conditions quite different from those in our solar system. This diversity suggests that habitable worlds might be more common than early estimates suggested. Climate modeling of exoplanets reveals the subtle ways that small changes in planetary parameters can lead to dramatically different outcomes for habitability. The presence or absence of continents, the tilt of a planet's rotational axis, the composition of its atmosphere, and the brightness of its star all interact in complex ways to determine whether a world can maintain liquid water at its surface over geological timescales. As we look toward the future of exoplanet science, several missions currently in development promise to revolutionize our understanding of potentially habitable worlds. The Nancy Grace Roman Space Telescope will search for exoplanets using gravitational microlensing, potentially discovering Earth-sized worlds orbiting at Earth-like distances from Sun-like stars. Ground-based, extremely large telescopes currently under construction will have the resolution to directly image some nearby exoplanets and study their atmospheric compositions in detail. The theoretical framework for understanding habitability continues to evolve as we discover more about the limits of life and the processes that shape planetary environments over cosmic time. Some researchers have proposed that habitability might be more common on worlds quite different from Earth, perhaps planets with global oceans and no continents, or worlds with atmospheres so thick that greenhouse warming allows surface liquid water even at great distances from their stars. The search for potentially habitable exoplanets has also sparked renewed interest in the rare Earth hypothesis, the idea that while simple life might be common in the universe, the specific sequence of events that led to complex life on Earth might be extraordinarily unlikely. This perspective suggests that while we might find many worlds harboring microbial life, planets with complex ecosystems or intelligent life might be vanishingly rare. Conversely, other researchers argue that life is a powerful force that can dramatically reshape planetary environments, potentially making planets more habitable over time rather than less. The evolution of photosynthesis on Earth not only changed our planet's atmospheric composition, but also helped stabilize its climate through feedback mechanisms that regulate global temperature. Similar processes on exoplanets might create increasingly habitable conditions as life evolves and spreads. The study of potentially habitable exoplanets intersects with questions about planetary protection and the ethics of interstellar exploration. If we do discover worlds harboring life, how should humanity respond? The protocols developed for Mars exploration, which aim to prevent contamination in both directions, would need to be extended and refined for interstellar missions to ensure that we don't inadvertently harm alien ecosystems or compromise scientific observations. The timescales involved in studying exoplanets remind us of the vast patience required for astronomical discovery. The nearest potentially habitable exoplanets are dozens of light years away, meaning that the light we observe from these worlds left their surfaces decades ago. We're seeing these planets as they were in the past, and any changes occurring now won't become visible to us for decades into the future. This temporal disconnect adds another layer of mystery to our exploration of distant worlds. The cultural and psychological impact of discovering potentially habitable exoplanets extends far beyond scientific circles. These discoveries tap into fundamental human desires to explore, to find our place in the universe, and to answer the ancient question of whether we're alone. The knowledge that there might be worlds where other forms of life have evolved, where different evolutionary paths have been taken, where entirely alien biospheres might exist, changes how we think about life, intelligence, and our own future as a species. Educational initiatives focused on exoplanets have captured public imagination in ways that few other scientific topics have managed. The ability to point to a star in the night sky and know that it hosts worlds potentially teeming with life creates a tangible connection between abstract astronomical concepts and the profound questions that drive human curiosity. Children growing up today are the first generation to live in a universe where we know with certainty that planetary systems are common and potentially habitable worlds exist in vast numbers. The international collaboration required for exoplanet science has created new models for sharing data, coordinating observations, and working together toward common scientific goals. Space-based telescopes like Kepler, TESS, and the James Webb Space Telescope represent investments by multiple nations in humanity's collective effort to understand our place in the cosmos. The discoveries made by these missions belong to all of humanity and help answer questions that transcend national boundaries and cultural differences. As we contemplate the potentially habitable exoplanets discovered so far, we're reminded that we're living through a unique moment in human history. For the first time, we have the technological capability to detect worlds that might harbor life and to begin characterizing their atmospheres and surface conditions. Future generations will likely look back on this era as the time when humanity first began to seriously grapple with the possibility that we're not alone in the universe. The search for life on exoplanets also drives technological innovation that benefits many aspects of human society. The precise measurements required to detect exoplanets have led to advances in optical systems, detector technology, and data analysis techniques that find applications in medical imaging, environmental monitoring, and industrial processes. The computational models used to understand exoplanet atmospheres help improve weather forecasting and climate modeling on Earth. The philosophical implications of potentially habitable exoplanets extend beyond questions of life's prevalence to touch on fundamental issues of meaning, purpose, and identity. If life has arisen independently on multiple worlds, what does this tell us about the nature of the universe and our own existence? Are there universal principles that govern the emergence and evolution of life? Or is each world's biological story unique and unrepeatable? The economic implications of exoplanet discoveries are only beginning to be understood. While these worlds are far too distant for any near-term exploitation of resources, the knowledge that potentially habitable planets exist in vast numbers might influence long-term planning for space exploration and development. Concepts for interstellar travel, once purely academic, are beginning to attract serious engineering attention and financial investment. The study of potentially habitable exoplanets has also highlighted the preciousness of Earth's biosphere and the delicate balance of conditions that maintain our planet's habitability. As we learn more about how rare or common Earth-like conditions might be in the universe, we gain a deeper appreciation for the complex web of factors that have allowed life to flourish on our world for billions of years. Climate change research has been informed by studies of exoplanet atmospheres and the processes that can lead to runaway greenhouse effects or global cooling. Venus and Mars provide cautionary tales of how planetary climates can evolve in directions incompatible with habitability, while exoplanet research reveals the range of atmospheric compositions and climate states possible for rocky worlds. The search for biosignatures in exoplanet atmospheres is pushing the boundaries of spectroscopic analysis and remote sensing technology. The techniques being developed to detect minute traces of oxygen, water vapor, and other potentially biological gases in the atmospheres of distant worlds might eventually find applications in monitoring Earth's environment, detecting industrial pollutants, and studying atmospheric chemistry in our own solar system. As our catalog of potentially habitable exoplanets continues to grow, patterns are beginning to emerge that help us understand the factors that contribute to planetary habitability. The size distribution of planets, the relationship between stellar type and planetary atmospheric retention, and the role of planetary system architecture in determining long-term stability all provide clues about where life might be most likely to arise and persist. The discovery of potentially habitable exoplanets has sparked new interdisciplinary collaborations between astronomers, biologists, geologists, and atmospheric scientists. Understanding habitability requires expertise from multiple fields, as the conditions necessary for life emerge from complex interactions between stellar radiation, planetary geology, atmospheric chemistry, and potentially biological processes themselves. The public fascination with potentially habitable exoplanets reflects deep human desires to understand our origins and destiny. These distant worlds represent possibilities, places where the story of life might be unfolding along completely different paths, where evolution has had billions of years to explore alternative solutions to the challenges of existence, where intelligence might have emerged in forms we can barely imagine. The naming conventions for exoplanets reflect both scientific systematization and human creativity. While most exoplanets receive catalog designations based on their host stars, some have been given more evocative names through public competitions and international astronomical unions. Names like Kepler-400 and 52 billion, or 2-715 b might seem technical, but they represent humanity's first attempts to catalog the worlds that might harbor our cosmic neighbors. The challenge of communicating exoplanet discoveries to the public requires balancing scientific accuracy with the natural human tendency to anthropomorphize distant worlds. While we must be careful not to overstate what we know about these planets' actual habitability, the excitement of discovery and the profound implications of potentially finding life beyond Earth make exoplanet science inherently compelling to wide audiences. The long-term implications of discovering inhabited exoplanets extend far beyond pure science. Such discoveries would likely influence philosophy, religion, literature, art, and virtually every aspect of human culture. The knowledge that life exists elsewhere in the universe would represent a watershed moment in human development, comparable to the Copernican revolution that displaced Earth from the center of the cosmos. The technological challenges of studying potentially habitable exoplanets continue to drive innovation in space-based instrumentation and data analysis. Future missions might deploy arrays of telescopes working together as interferometers, capable of directly imaging Earth-sized planets around nearby stars and analyzing their atmospheric compositions in extraordinary detail. These observations might reveal seasonal changes, weather patterns, and perhaps even signs of vegetation or other large-scale biological processes. The statistical analysis of exoplanet populations is beginning to provide insights into the frequency of potentially habitable worlds in our galaxy. Early estimates suggest that billions of planets might exist in the habitable zones of their stars, with Earth-sized worlds around Sun-like stars being particularly interesting targets for detailed study. However, the fraction of these worlds that actually maintain habitable surface conditions remains uncertain. The study of exoplanet evolution over cosmic time reveals the dynamic nature of planetary habitability. Worlds that are habitable today might not remain so indefinitely, while planets that currently seem inhospitable might develop habitable conditions as their stars evolve and their atmospheric compositions change. This temporal dimension adds complexity to our understanding of where and when life might arise in the universe. The role of asteroid and comet impacts in shaping exoplanet habitability parallels what we know about the history of life on Earth. While large impacts can cause mass extinctions and temporarily disrupt habitable conditions, they also deliver water and organic compounds to planetary surfaces and might actually enhance habitability over long timescales by driving geological activity and atmospheric evolution. The search for potentially habitable exoplanets has revealed the incredible diversity of planetary systems in our galaxy. From hot Jupiters that orbit their stars in days to cold worlds that take centuries to complete a single orbit, from planets with diamond rain to worlds covered in global oceans, the universe's creativity in forming worlds exceeds anything early science fiction imagined. As we continue to discover and characterize potentially habitable exoplanets, we're building a foundation for one of humanity's greatest adventures: the eventual exploration of other worlds that might harbor life. The mathematics of interstellar travel remind us of the vast scales involved in exploring these distant worlds. Even traveling at 1% the speed of light, a velocity far beyond our current capabilities, the journey to the nearest potentially habitable exoplanet would take over 400 years. Yet these seemingly insurmountable distances have not dampened human enthusiasm for eventual interstellar exploration. Instead, they've inspired new approaches to space travel and communication that push the boundaries of physics and engineering. Concepts for generation ships, spacecraft designed to support human crews across multiple lifetimes, represent one approach to interstellar exploration. These massive vessels would need to create self-sustaining ecosystems capable of maintaining not just human life, but entire biospheres during journeys lasting centuries or millennia. The challenges are staggering: maintaining genetic diversity in small populations, preserving knowledge and culture across generations, managing psychological and social dynamics in confined spaces, and ensuring that complex life support systems remain functional over timescales much longer than any human institution has yet survived. The alternative approach of sending robotic probes to nearby exoplanets faces different but equally daunting challenges. These spacecraft would need to be incredibly lightweight to achieve the velocities necessary for reasonable transit times, yet sophisticated enough to conduct meaningful scientific observations upon arrival. They would need to communicate across interstellar distances, transmitting data back to Earth across decades or centuries, while remaining functional in the harsh environment of space. The search for potentially habitable exoplanets has also inspired research into more exotic propulsion concepts. Solar sails that harness the momentum of light, fusion rockets that might achieve significant fractions of light speed, and even theoretical concepts like Bussard ramjets that would collect interstellar hydrogen as fuel, all represent attempts to solve the fundamental problem of crossing the vast distances between stars in reasonable amounts of time. Perhaps more immediately achievable than physical travel to exoplanets is the possibility of communication with any intelligent civilizations that might exist on these distant worlds. The search for extraterrestrial intelligence, or SETI, has been listening for artificial radio signals from space for decades. But the discovery of potentially habitable exoplanets has provided new targets for these efforts. If technological civilizations exist on nearby exoplanets, they might be using radio waves, laser pulses, or other forms of electromagnetic communication that we could detect with sufficiently sensitive instruments. The protocols for responding to potential signals from exoplanets raise fascinating questions about humanity's role as a cosmic citizen. Should we attempt to communicate with alien civilizations? And if so, what should we say? How do we represent human culture, knowledge, and values to intelligences that evolved under completely different conditions? These questions, once purely theoretical, have taken on new urgency as we discover more worlds where intelligence might have evolved. The influence of potentially habitable exoplanets on human culture extends beyond science and technology into art, literature, and philosophy. Science fiction has always speculated about alien worlds, but the discovery of actual exoplanets has provided concrete targets for imagination. Writers can now craft stories about specific worlds. Proxima Centauri b with its red dwarf sun, the TRAPPIST T-1 planets with their complex orbital dance, or Kepler 452 billion with its long seasons under a sun-like star. Artists have begun creating visualizations of these distant worlds based on scientific data and theoretical models. These artistic interpretations help make abstract astronomical discoveries tangible and emotionally resonant for the general public. The crimson skies of planets orbiting red dwarf stars, the exotic weather patterns of tidally locked worlds, and the alien beauty of multiple suns rising over strange landscapes all provide new subjects for creative expression. The philosophical implications of potentially habitable exoplanets continue to unfold as our understanding deepens. If life is common in the universe, as the abundance of potentially habitable planets suggests, then Earth's biosphere might be just one of countless experiments in biological evolution. Each inhabited world would represent a different solution to the challenges of existence, a different path through the vast space of evolutionary possibilities. The concept of convergent evolution, the tendency for unrelated organisms to evolve similar traits when facing similar environmental challenges, might apply on a cosmic scale. If life exists on exoplanets, it might have independently evolved solutions to problems similar to those faced by life on Earth. Flight, photosynthesis, intelligence, and social cooperation might be universal features of complex life, arising independently on worlds separated by dozens of light years. Alternatively, the specific history of each world might lead to forms of life so alien that we would barely recognize them as living organisms. The particular chemistry of an exoplanet's atmosphere, the spectrum of light from its star, the strength of its gravity, and countless other factors might push evolution down paths that have no parallel on Earth. Life on a high-gravity super-Earth might be predominantly flat and sprawling. Organisms on a world with a methane-rich atmosphere might be based on completely different biochemistry. intelligence might emerge in forms that bear no resemblance to anything in Earth's biosphere. The study of potentially habitable exoplanets has also highlighted the role of chance in shaping planetary evolution. Small changes in initial conditions, the size of a planet's core, the timing of major impacts, the presence or absence of large moons, can lead to dramatically different outcomes over billions of years. This sensitivity to initial conditions suggests that each potentially habitable world represents a unique natural experiment in planetary evolution. The concept of planetary engineering, or terraforming, has gained new relevance as we identify worlds that might be made more habitable through technological intervention. While the distances to exoplanets make any near-term terraforming efforts impossible, understanding the factors that control planetary habitability might eventually allow future civilizations to modify worlds to better support life. Such projects would require timescales measured in millennia and resources that dwarf anything humanity has yet undertaken. The discovery of potentially habitable exoplanets has also influenced our approach to protecting Earth's environment. Seeing our planet in the context of the vast catalog of exoplanets helps emphasize both Earth's preciousness and its fragility. We are, as far as we know, the only world in the universe where complex life definitely exists, where consciousness has emerged, where intelligence has developed technology capable of studying other worlds. This knowledge carries with it a profound responsibility to preserve the conditions that have allowed Earth's biosphere to flourish. Climate science has been enriched by studies of exoplanet atmospheres and the various ways planetary climates can evolve. The runaway greenhouse effect that turned Venus into a hellish world provides a cautionary example of how planetary climates can shift irreversibly. Conversely, the discovery of potentially habitable planets around red dwarf stars has revealed new mechanisms for climate stability that might operate over much longer timescales than the processes that regulate Earth's climate. The search for biosignatures in exoplanet atmospheres represents humanity's first serious attempt to test whether life is unique to Earth. The detection of oxygen and water vapor together in an exoplanet's atmosphere would provide compelling evidence for biological processes, while the simultaneous presence of oxygen and methane would be even more convincing, since these gases react with each other and disappear quickly unless constantly replenished by biological activity. However, distinguishing between biological and non-biological processes that might produce similar atmospheric signatures requires sophisticated modeling and multiple independent lines of evidence. Oxygen can be produced by the breakdown of water molecules in a planet's upper atmosphere, while methane can be generated by geological processes. Only by carefully studying the atmospheric chemistry, seasonal variations, and other characteristics of potentially habitable exoplanets can we hope to identify definitive signs of life. The instruments being developed to study exoplanet atmospheres represent marvels of precision engineering. Spectrographs capable of detecting the minute absorption lines caused by trace gases in exoplanet atmospheres must be stable enough to make measurements over months or years, sensitive enough to detect signals 1 billion times fainter than their host stars, and sophisticated enough to distinguish between different molecules that might produce similar spectroscopic signatures. Future missions designed to study potentially habitable exoplanets will require unprecedented international cooperation and long-term commitment. The timescales involved in characterizing these distant worlds, decades to complete comprehensive atmospheric studies, centuries to detect long-term changes, exceed the typical planning horizons of most human institutions. Success will require sustained commitment across generations, something humanity has rarely achieved for scientific endeavors. The educational value of exoplanet research extends far beyond astronomy into virtually every scientific discipline. Understanding planetary habitability requires knowledge of physics, chemistry, biology, geology, and atmospheric science. The interdisciplinary nature of exoplanet research makes it an ideal vehicle for teaching scientific thinking and demonstrating how different fields of knowledge interconnect to address fundamental questions. The discovery of potentially habitable exoplanets has also sparked new interest in astrobiology, the study of life in the universe. This emerging field brings together researchers from diverse backgrounds to address questions that once belonged purely to science fiction. How did life arise on Earth? What are the minimal requirements for habitability? How might life evolve under conditions different from those on Earth? Could we recognize life based on fundamentally different chemistry? The methodological challenges of astrobiology are particularly intriguing because we have only one example of life, Earth's biosphere, from which to generalize about life elsewhere. This sample size of one makes it difficult to distinguish between universal principles and local accidents in the history of life on Earth. The discovery of life on exoplanets would provide the additional data points necessary to begin understanding which aspects of Earth's biology reflect general principles and which are unique to our particular world. The psychological impact of discovering inhabited exoplanets would likely be profound and long-lasting. The knowledge that we're not alone in the universe would fundamentally change human perspectives on existence, meaning, and our place in the cosmic order. Such a discovery might promote greater global unity by providing a shared focus for human attention and resources. Or it might exacerbate existing divisions by raising questions about how humanity should respond to the knowledge of alien life. The religious and spiritual implications of finding life on exoplanets would vary enormously across different belief systems and cultures. Some might see the discovery of alien life as confirmation of the universe's creative abundance, while others might struggle to reconcile such discoveries with existing theological frameworks. The diversity of potentially habitable exoplanets suggests that if life exists elsewhere, it might have evolved along paths quite different from those taken on Earth. The legal and ethical frameworks for dealing with the discovery of life on exoplanets remain largely undeveloped. Who would have the authority to speak for humanity in responding to signals from alien civilizations? How should we balance scientific curiosity with caution about potentially dangerous contact? What rights might alien life forms have, and how should we weigh their interests against human goals and desires? The timeline for definitively detecting life on exoplanets remains uncertain, but is likely measured in decades rather than centuries. The James Webb Space Telescope and other current missions are already capable of detecting some biosignatures in the atmospheres of nearby exoplanets. Future missions with even greater sensitivity and resolution will expand our ability to study these distant worlds in unprecedented detail. The possibility of detecting not just life, but signs of intelligence on exoplanets adds another layer of complexity and excitement to these searches. Large-scale engineering projects, artificial illumination of planetary night sides, or deliberate modification of atmospheric chemistry might be detectable by future telescopes. The discovery of technological civilizations on nearby exoplanets would raise questions about the prevalence of intelligence in the universe and the typical pathways by which consciousness emerges from simpler forms of life. The study of potentially habitable exoplanets has revealed the incredible diversity of conditions under which life might arise and persist. From the tidally locked worlds of red dwarf stars to the massive super-Earths with crushing gravity, from planets with exotic atmospheric compositions to worlds orbiting binary star systems, the universe offers environments for life that stretch far beyond anything early researchers imagined. This diversity suggests that habitability might be more common than originally thought, but it also highlights the complex web of factors that determine whether a world can actually support life over geological timescales. Temperature, atmospheric composition, magnetic fields, geological activity, stellar stability, and countless other variables must all align in ways that allow liquid water to persist and complex chemistry to flourish. The search for potentially habitable exoplanets has also emphasized the importance of time in understanding planetary evolution. Worlds that appear habitable today might not have been habitable in the past, or might not remain habitable in the future. Conversely, planets that currently seem hostile might develop more favorable conditions as their stars evolve or their atmospheres change. This temporal dimension adds richness and complexity to our understanding of where life might exist in the universe. As we peer deeper into space and further back in time, we're discovering exoplanets around stars that formed when the universe was much younger and had different chemical compositions than today's stars. These ancient worlds might have experienced very different conditions during their formation and early evolution, potentially leading to alternative pathways for the emergence of life. The oldest potentially habitable exoplanets might harbor life forms that have had billions more years to evolve than anything on Earth. The cultural impact of exoplanet discoveries continues to ripple through human society in ways both obvious and subtle. Children growing up today take for granted the existence of thousands of known exoplanets, including many that might harbor life. This knowledge shapes their understanding of humanity's place in the universe in ways that differ fundamentally from previous generations who grew up believing that planetary systems might be rare cosmic accidents. The international cooperation required for exoplanet research has created new models for sharing scientific resources and coordinating observations across national boundaries. The data collected by space-based telescopes like Kepler and TESS are made freely available to researchers worldwide, enabling collaborative analysis that no single institution could accomplish alone. This open approach to scientific data reflects the recognition that questions about life in the universe transcend national interests and belong to all humanity. The economic implications of exoplanet research extend beyond the immediate costs of missions and instruments to encompass the broader value of expanding human knowledge and capabilities. The technologies developed for detecting and characterizing exoplanets often find applications in other fields, from medical imaging to environmental monitoring. The mathematical and computational techniques used to analyze exoplanet data contribute to advances in artificial intelligence, signal processing, and statistical analysis. The long-term implications of discovering inhabited exoplanets might include fundamental changes in how humanity allocates resources and sets priorities. If we determine that life is common in the universe, this might shift emphasis toward preserving Earth's unique biosphere and developing sustainable ways of living on our home planet. Alternatively, the knowledge that habitable worlds exist elsewhere might inspire greater investment in space exploration and eventual interstellar travel. The philosophical questions raised by potentially habitable exoplanets touch on some of humanity's deepest concerns about existence, purpose, and meaning. If life arises readily wherever conditions allow, This might suggest that the universe has a tendency toward increasing complexity and consciousness. Alternatively, if life proves to be rare despite the abundance of potentially habitable worlds, this might emphasize the preciousness of consciousness and the importance of preserving it wherever it arises. The study of exoplanet atmospheres has revealed the delicate balance of chemical processes that maintain habitability over geological timescales. On Earth, the carbon cycle regulates global temperature by controlling the amount of carbon dioxide in the atmosphere through weathering, volcanism, and biological processes. Similar feedback mechanisms on exoplanets might help maintain stable climates, but the specific details would depend on each world's unique characteristics. The role of stellar evolution in determining exoplanet habitability adds another temporal dimension to these considerations. Stars like our Sun gradually become brighter as they age, potentially pushing initially habitable planets out of the habitable zone over billions of years. Red dwarf stars, in contrast, remain stable for trillions of years, potentially providing much longer windows for the evolution of complex life. However, these same red dwarfs often produce dangerous flares that might strip away planetary atmospheres or sterilize surface environments. The discovery of potentially habitable exoplanets has highlighted the importance of planetary protection protocols for future space missions. If we eventually develop the capability to send probes to nearby exoplanets, we'll need to ensure that these missions don't contaminate alien biospheres with Earth life or compromise our ability to study indigenous life. By introducing foreign organisms, the challenges of maintaining sterile spacecraft over interstellar distances and operational lifetimes of centuries or millennia are formidable. As we contemplate the vast catalog of potentially habitable exoplanets now known to exist, we're reminded that we're living through an extraordinary moment in human history. Previous generations could only wonder whether other worlds existed beyond our solar system. Today, we know with certainty that planets are common throughout our galaxy, and that many of these worlds exist under conditions that might allow life to flourish. The next few decades will likely bring the first definitive detections of life beyond Earth, whether in the form of biosignatures in exoplanet atmospheres, subsurface oceans on moons in our solar system, or perhaps even signals from technological civilizations. These discoveries will mark humanity's transition from a species confined to a single world to cosmic citizens aware of our place in a universe teeming with life and possibility. The potentially habitable exoplanets we've discovered so far represent just the beginning of our exploration of the cosmic community. Each of these distant worlds tells a unique story of planetary formation, evolution, and the conditions that might allow life to emerge from chemistry. As our instruments become more sensitive and our analysis techniques more sophisticated, we'll undoubtedly discover worlds that challenge our current understanding of habitability and expand our conception of where life might exist. In the quiet moments before sleep, when consciousness begins to fade and the mind drifts toward dreams, we can contemplate these distant worlds where other forms of awareness might be experiencing their own versions of this universal transition from waking to sleeping. Perhaps under the crimson light of a red dwarf star, or in the complex shadows cast by binary suns, other intelligences pause in their activities to rest and dream, just as we do under our familiar yellow sun. The search for potentially habitable exoplanets connects us to questions that have fascinated humanity since we first looked up at the night sky and wondered whether we're alone. These distant worlds, separated from us by vast reaches of space and time, remind us that our cosmic story is part of a much larger narrative, one written in the language of stars and planets, of evolution and consciousness, of the endless creativity that emerges when matter and energy dance together across the vastness of space. As you drift toward sleep tonight, you might imagine yourself standing on one of these distant worlds, watching unfamiliar constellations wheel overhead, breathing air that might carry the sense of alien life forms, feeling the gentle pull of a different gravity, experiencing the profound peace that comes from knowing that life, in all its wonderful diversity, might fill the universe with intelligence, creativity, and the same quiet wonder that now carries you gently into dreams. The cosmos is vast and ancient, filled with worlds we're only beginning to discover and understand. Among those distant lights that shine in the darkness, there may be planets where other dreamers rest under alien skies, connected to us not by space or time, but by the universal experience of consciousness, contemplating its place in the infinite mystery of existence. The gentle rhythm of discovery continues, like waves lapping at the shore of human knowledge. Each new exoplanet we detect adds another verse to the cosmic poem we're slowly learning to read. The light from these distant worlds has traveled for years, decades, sometimes centuries to reach our telescopes, carrying with it information encoded in wavelengths and frequencies that tell stories of atmospheric composition, surface temperature, and orbital dynamics. This light is a messenger from distant realms, whispering secrets about conditions that might nurture life in forms we can barely imagine. Consider the patience inherent in this cosmic correspondence. The photons of light we analyze today began their journey from these exoplanets when our own world was a different place entirely. Light now reaching us from the TRAPPIST-T-, one system, left those 7 worlds when Earth was still emerging from the last ice age, when our ancestors were beginning to develop agriculture and settle into permanent communities. The information we gather today about these distant planets captures moments from decades past, creating a temporal bridge between our present curiosity and their ancient light. This time delay adds a dreamlike quality to our exploration of exoplanets. We observe these worlds not as they are now, but as they were when their light began its long journey through the interstellar medium. By the time we develop the technology to visit these planets, assuming we ever do, they will have continued evolving for additional decades or centuries beyond what we observe today. We are explorers not just of distant space, but of distant time, archaeological investigators studying the preserved light of other worlds. The mathematics of exoplanet detection reveal the extraordinary precision required to find these distant worlds. The Kepler Space Telescope monitored over 150,000 stars simultaneously, measuring their brightness with such accuracy that it could detect changes of less than 0.01%, equivalent to detecting the dimming caused by a fruit fly passing in front of a car's headlight from several miles away. This level of precision required instruments stable enough to maintain calibration over years of continuous operation, while orbiting Earth at thousands of miles per hour. The data processing challenges for exoplanet missions involve sifting through vast amounts of information to find the subtle patterns that reveal planetary transits. Each star monitored by Kepler-generated brightness measurements every 30 minutes for nearly 4 years, creating datasets containing millions of individual measurements. Identifying genuine planetary signals among this ocean of data requires sophisticated algorithms that can distinguish between real planetary transits and false signals caused by stellar activity, instrumental artifacts, or background interference. The statistical analysis of exoplanet populations has revealed patterns that help us understand the typical outcomes of planetary formation processes. Small planets appear to be much more common than large ones, with Earth-sized worlds and super-Earths far outnumbering gas giants in most stellar systems. This size distribution suggests that the processes that build rocky planets are highly efficient, while the conditions necessary to form gas giants are more restrictive and depend on specific timing during the planet formation process. The orbital architectures of exoplanet systems show remarkable diversity compared to our solar system's relatively orderly arrangement. Many systems contain planets packed much more tightly than the worlds orbiting our Sun, with multiple planets crowded into orbits that would fit within Mercury's path around our star. These compact systems challenge our understanding of how planets migrate during formation and raise questions about the long-term stability of such densely packed arrangements. The phenomenon of planetary migration has emerged as a crucial factor in determining the final configuration of exoplanet systems. During the early phases of system formation, when young planets are still embedded in the disk of gas and dust surrounding their star, gravitational interactions can cause planets to spiral inward or outward from their original formation locations. This migration process can move potentially habitable planets into or out of their star's habitable zone, fundamentally altering their prospects for supporting life. Hot Jupiters, gas giant planets that orbit extremely close to their stars, likely formed much further out in their systems before migrating inward to their current positions. This migration process might have disrupted the formation of smaller, rocky planets in the inner regions of these systems, potentially preventing the development of Earth-like worlds. However, some hot Jupiters might have migrated inward after terrestrial planets had already formed and stabilized, creating systems where Earth-like worlds coexist with giant planets on scorching close orbits. The concept of habitable moons has gained increasing attention as we've discovered gas giant planets orbiting within their stars' habitable zones. These worlds might host large moons that could maintain liquid water on their surfaces while benefiting from tidal heating generated by their gravitational interaction with the parent planet. Such moons might actually be more habitable than isolated planets because tidal heating could maintain geological activity and help regulate surface temperature even as the host star evolves and changes brightness over cosmic time. The potential for life in subsurface oceans on exoplanet moons opens up entirely new categories of habitable environments. Just as Jupiter's moon Europa and Saturn's moon Enceladus harbor vast oceans beneath their icy crusts, heated by tidal forces from their parent planets, similar processes might occur in exoplanet systems. These hidden oceans could remain liquid and potentially habitable, even on moons orbiting planets far outside their star's traditional habitable zone. The study of stellar activity and its impact on exoplanet habitability reveals the complex relationship between stars and their planetary companions. Many stars, particularly young ones and red dwarfs, produce powerful flares that can temporarily increase their brightness by factors of 10 or more. These flares emit intense ultraviolet and X-ray radiation that can strip away planetary atmospheres over time, potentially rendering initially habitable worlds lifeless and barren. However, stellar flares might also play positive roles in the development of life on exoplanets. The energetic radiation from flares could drive atmospheric chemistry in ways that promote the formation of complex organic molecules. Some researchers have suggested that moderate levels of flare activity might actually enhance habitability by providing energy for chemical reactions, while remaining below the threshold that would completely strip away planetary atmospheres. The magnetic field interactions between exoplanets and their host stars create another layer of complexity in assessing habitability. Planets with strong magnetic fields might be better protected from stellar radiation, but they could also experience enhanced heating through magnetic reconnection events with the stellar magnetic field. The radio emissions generated by these magnetic interactions might eventually be detectable by Earth-based radio telescopes, providing a new method for studying exoplanet properties. The atmospheric escape, processes that determine whether exoplanets can retain their atmospheres over geological timescales, depend on a complex interplay of factors, including planetary mass, atmospheric composition, stellar radiation, and magnetic field strength. Low-mass planets have weaker gravitational fields and are more susceptible to atmospheric loss, while planets with thick atmospheres might be able to resist erosion even under intense stellar radiation. Understanding these processes is crucial for determining which potentially habitable exoplanets are likely to have maintained the atmospheric conditions necessary for life. The role of water in planetary formation and evolution extends far beyond its importance as a solvent for biological processes. Water ice serves as a key building material for planetary cores in the outer regions of forming stellar systems, and the locations where water can condense, marked by the snow line in protoplanetary disks, influence the sizes and compositions of planets that form at different distances from their stars. The amount of water delivered to potentially habitable planets during their formation history might determine whether they develop into ocean worlds, desert planets, or something in between. The greenhouse effect on exoplanets can operate through mechanisms quite different from those on Earth, depending on the atmospheric composition and stellar spectrum. Carbon dioxide remains an important greenhouse gas around most types of stars, but water vapor, methane, and other molecules might dominate greenhouse warming on planets with different atmospheric chemistries. Some exoplanets might maintain habitable surface temperatures through greenhouse warming by molecular hydrogen, a process that doesn't occur on Earth, but might be important for planets with thick primordial atmospheres. The concept of snowball and runaway greenhouse states represents two extremes of climate evolution that could affect exoplanet habitability. Snowball states occur when a planet's surface becomes completely frozen, with ice reflecting so much sunlight that warming becomes impossible, until external factors like volcanic outgassing change atmospheric composition. Runaway greenhouse states develop when atmospheric greenhouse warming becomes so intense that water vapor is lost to space, creating conditions like those on present-day Venus. The feedback mechanisms that help maintain stable climates on habitable planets operate through complex interactions between atmospheric composition, surface temperature, weathering processes, and potentially biological activity. On Earth, the carbonate silicate cycle helps regulate global temperature over geological timescales by controlling atmospheric carbon dioxide levels through the balance between volcanic outgassing and chemical weathering of rocks. Similar processes might operate on exoplanets, but the specific mechanisms would depend on each world's unique geological and atmospheric characteristics. The search for technosignatures, evidence of technological activity on exoplanets, represents an extension of traditional SETI research into the realm of exoplanet science. Future telescopes might be able to detect industrial pollutants in exoplanet atmospheres, artificial illumination of planetary night sides, or large-scale engineering projects that modify planetary environments. These observations could provide evidence for technological civilizations, even if they're not actively transmitting radio signals toward Earth. The Drake equation, formulated in 1961 to estimate the number of communicating civilizations in our galaxy, has been refined and updated as our knowledge of exoplanets has expanded. The discovery that planets are common around most stars has increased estimates for some terms in the equation, but uncertainties remain about the fraction of planets where life actually arises and evolves to intelligence. The potentially habitable exoplanets we've discovered provide concrete targets for testing these theoretical frameworks. The Fermi paradox, the apparent contradiction between the high probability of extraterrestrial life and the lack of evidence for its existence, takes on new dimensions in light of exoplanet discoveries. If potentially habitable planets are common, why haven't we detected signs of life or intelligence among the thousands of worlds we've discovered? Possible explanations range from the rarity of complex life to the possibility that technological civilizations tend to be short-lived or prefer to remain undetectable. The biological implications of different types of stellar radiation extend beyond simple questions of temperature to encompass the specific wavelengths of light available for photosynthesis and other biological processes. Plants around red dwarf stars might evolve photosynthetic systems optimized for infrared radiation, potentially appearing very dark or even black to human eyes. Life around more massive, bluer stars might face challenges from increased ultraviolet radiation, but could potentially harness the greater energy available in shorter wavelength light. The potential for panspermia, the transfer of life between planets, might be enhanced in some exoplanet systems, particularly those with multiple worlds orbiting close together. Asteroid or comet impacts on one planet could launch material into space that eventually reaches neighboring worlds, potentially spreading life throughout an entire stellar system. This process might be especially important in compact systems like TRAPPIST-T-1, where the travel time between planets would be much shorter than the typical timescales for biological extinction. The study of exoplanet compositions through transit spectroscopy and other techniques is beginning to reveal the chemical diversity of worlds beyond our solar system. Some planets appear to have atmospheres dominated by water vapor, while others show evidence for exotic clouds made of minerals like corundum or perovskite. These observations provide insights into the formation histories of different worlds and the range of conditions under which planets can maintain substantial atmospheres. The thermal evolution of exoplanets over cosmic time influences their potential for habitability in ways that depend on planetary mass, composition, and orbital characteristics. Small planets cool more quickly than large ones, potentially leading to the cessation of geological activity that helps maintain atmospheric pressure and composition. However, tidal heating from gravitational interactions with other planets or moons might provide alternative energy sources that keep small worlds geologically active for much longer periods. The role of planetary obliquity, the tilt of a planet's rotation axis relative to its orbital plane, in determining climate stability, has important implications for exoplanet habitability. Earth's moderate obliquity of about 23 degrees creates our familiar seasons and helps maintain relatively stable climate conditions over geological time. Planets with extreme obliquities might experience chaotic seasonal variations that make long-term habitability difficult, while worlds with very small obliquities might lack the climate diversity that promotes biological innovation. The possibility of detecting aurora on exoplanets opens up new avenues for studying planetary magnetic fields and their interactions with stellar winds. Aurora occur when charged particles from a star interact with a planet's magnetic field, creating light emissions in the upper atmosphere. Observing these phenomena on exoplanets could provide information about magnetic field strength and structure, atmospheric composition, and the intensity of stellar particle radiation. The long-term evolution of stellar systems affects exoplanet habitability through mechanisms that operate over billions of years. As stars age and evolve, they gradually increase in brightness, potentially pushing initially habitable planets out of the habitable zone. However, this same stellar evolution might make more distant planets habitable, creating a moving habitable zone that could support life on different worlds at different times in a system's history. The potential for detecting seasonal variations on exoplanets represents one of the most exciting frontiers in exoplanet characterization. Changes in atmospheric composition, cloud cover, or surface properties over the course of a planet's orbital period could indicate active weather systems, seasonal vegetation cycles, or other dynamic processes. Such observations would provide unprecedented insights into the day-to-day reality of conditions on these distant worlds. The study of binary and multiple star systems has revealed that planets can form and remain stable even in these complex gravitational environments. Some planets orbit both stars of a binary system, experiencing 2 sunrises and sunsets each day, while others orbit just one star in a binary pair. The gravitational dynamics of these systems create unique challenges for planetary formation and evolution, but they might also provide interesting opportunities for enhanced habitability through additional heating from companion stars. The atmospheric chemistry of exoplanets in extreme environments pushes the boundaries of our understanding of what constitutes a habitable world. Planets with surface pressures hundreds of times greater than Earth's might maintain liquid water at temperatures well above the normal boiling point, while worlds with very thin atmospheres might support liquid water only in protected locations, like deep valleys or crater floors, where atmospheric pressure is slightly enhanced. The search for amino acids and other organic compounds in exoplanet atmospheres represents a potential pathway to detecting the chemical building blocks of life before finding life itself. These complex molecules could form through non-biological processes in planetary atmospheres, but their detection would indicate the presence of the chemical ingredients necessary for biological evolution. Future telescopes might be sensitive enough to detect spectroscopic signatures of these organic compounds in the atmospheres of nearby exoplanets. The cultural and social implications of discovering life on exoplanets extend into questions about how such discoveries might change human behavior, priorities, and self-perception. The knowledge that life exists elsewhere in the universe might promote greater environmental consciousness on Earth, increased international cooperation in space exploration, or renewed interest in long-term thinking about humanity's future. Alternatively, such discoveries might have little immediate impact on daily life, while gradually reshaping philosophical and religious perspectives over generations. The economic analysis of exoplanet research reveals both the substantial costs involved in these investigations and the potential long-term benefits that might result from the knowledge gained. While the direct economic returns from exoplanet science are minimal in the near term, the technological developments required for these missions often find applications in other fields, and the fundamental knowledge gained contributes to our understanding of planetary formation, evolution, and habitability in ways that might eventually prove valuable for understanding Earth's own future. The educational applications of exoplanet science continue to evolve as new discoveries capture public imagination and provide concrete examples for teaching concepts in physics, chemistry, biology, and mathematics, the ability to point to specific exoplanets and discuss their properties, potential for habitability, and the methods used to study them makes abstract scientific concepts more tangible and engaging for students at all levels. The philosophical questions raised by potentially habitable exoplanets touch on fundamental issues about the nature of life, consciousness, and intelligence in the universe. If life is common, what does this tell us about the underlying principles that govern the emergence of biological complexity? If intelligence arises independently on multiple worlds, might there be universal aspects to consciousness and reasoning that transcend the specific evolutionary histories of different planets? As we continue to contemplate these distant worlds and their potential for hosting life, we're reminded that the universe operates on scales of space and time that dwarf human experience, yet somehow gave rise to beings capable of contemplating infinity. The potentially habitable exoplanets we've discovered represent islands of possibility in the cosmic ocean, worlds where the same physical laws that govern our own planet might have written different stories of evolution, adaptation, and perhaps awareness. The night sky that has inspired human wonder for millennia now holds a deeper meaning. Those points of light are no longer mysterious fires hanging in a celestial sphere, but distant suns surrounded by worlds that might harbor their own forms of life, their own stories of emergence from chemistry to biology, to perhaps even consciousness. Under different stars, in the light of red dwarfs, or the complex illumination of binary systems, other forms of awareness might pause to contemplate the same questions that occupy our thoughts. What is our place in this vast cosmos? Are we alone? What mysteries await discovery in the endless darkness between the stars? Sleep well, knowing that you're part of this grand cosmic story, connected across the light years to worlds where similar stories might be unfolding, where other dreamers might rest under alien skies, sharing with us the profound mystery of consciousness arising from stardust, to contemplate the infinite universe that gave it birth. Tomorrow will bring new discoveries, new worlds, and new reasons to marvel at the extraordinary cosmos we call home, where planets dance around distant stars, and life writes its poetry in chemicals and time, creating endless variations on the theme of existence itself.